Hello guys, good morning. Good morning to all of you. Is everything all right? To all of you. So today we'll be discussing the second part of time independent perturbation theory. So without any further ado, if everything is all right, let's start with the problem. Okay, I gave you this problem as homework. Let's start with this. The ground state eigenfunction for the potential V of x is equals to minus delta x, where delta x is the delta function, is given by psi of x is equals to a to the power minus alpha mod x, where a and alpha are constant, alpha greater than 0. If a perturbation bx to the power 4 is applied, the first order correction to the energy of the ground state will be. Good morning, Harry, Murli. How are you all, guys? Could you solve this problem? Look, the given wave function is not normalized. A to the power minus alpha mod x. So if you calculate the normalized wave function, this is a common wave function. The normalized wave function will be psi of x. This unknown constant is found out to be alpha. Okay. So if you want to calculate the first order correction to the energy of the ground state. Good morning, Karthik. Ground state means what? E1, let's say E1 1. And ground state wave function is given to you. So you can just put it, let's say psi 1 h prime psi 1. So it is psi x, it is given in the form of psi x, so let's write psi h prime psi. So this is nothing but minus infinity to plus infinity. Psi star and psi are the same, so it is alpha to the power minus 2 alpha mod x, and h prime is bx to the power 4 dx. Okay. So this is how much? Could you calculate this? Look here, if you put x is equals to minus x, this what is this kind of function overall? If I consider, let's say e to the power minus 2 alpha mod x, and a alpha b are constant, x to the power 4. This function as a whole, it is an even function undoubtedly, right? If you put f of minus x is equals to, if you calculate this f of minus x, you will get f of x. Okay, for this. So that is why it is an even function. If it is an even function, we can write it as 2 times 0 to infinity alpha bx to the power 4 to the power minus 2 alpha mod x dx. Now we do not need to write mod x because we have taken the positive values of x, 0 to alpha, 0 to infinity. So mod x can be replaced by simple x. Okay, now you know the formula. You know this standard formula, 0 to infinity x to the power n e to the power minus alpha x dx. This is nothing but n factorial by alpha to the power n plus 1. So as a result of that, if you use this standard integration, we can write e1 of 1 is equals to 2 alpha integration this. What is this value? Okay, let's take beta outside also. 2 alpha beta, n is equals to 4. So 4 factorial divided by alpha is equals to how much? Alpha is equals to minus 2 alpha here. Sorry, minus plus. So 2 alpha to the power n plus 1, 4 plus 1. So what is this value? Two alpha beta into 4 factorial. 4 factorial means 4 into 3, 12, 12, 24. 2 into 24 alpha beta divided by 2 to the power 5. Okay, into alpha to the power 5. So this is how much? Three b divided by 2 alpha to the power 4. Is it clear? Option B. Any question, guys? Could you understand the first part? Why root alpha is coming? Calculation for root alpha. So this is just note for the normalization part. How do you do the normalization? I'm just showing you how you got the normalization done. Psi of x is equals to a e to the power minus alpha mod x. So normalization condition we can use here. Minus infinity plus infinity mod psi square tx is equals to 1. This is what the normalization condition is. So this becomes a square minus infinity plus infinity to the power minus 2 alpha mod x tx is equals to 1. So this is an even function. So 2a square 0 to infinity to the power minus 2 alpha x dx. 2a square, and it is e to the power minus 2 alpha x by minus 2 alpha 0 to infinity. So now if you put, you will get it 2a square into, it is 1 by 2 alpha, this is 1. So 2 get cancelled, so a is equals to square root of alpha, and that is why the sign normalized is written as square root of alpha e to the power minus alpha mod x. So this is just for your reference, okay, simple thing. Let's go to the next problem. The perturbation, same perturbation bx to the power 4, where b is a constant, is added to the one dimensional harmonic oscillator potential. Now you are given harmonic oscillator potential system, which of the following denotes the correction to the ground state energy. You have to find out the correction to the ground state energy to the first order, and possible necessary information like the ground state wave function is given to you. Although I have told you to remember this ground state wave function, but here fortunately you have been given, but it will be better if you can remember the ground state wave function of harmonic oscillator, 1D harmonic oscillator. So you can use this standard integration as well if you want. So can you solve this problem? So the correction to the ground state energy, to the ground state energy to first order is given by, how will you give? Ground state energy E0, what is the correction? First order correction, so 1. Okay, this is the formula is psi 0 h prime psi 0, is simple as that, where your psi 0 is m omega by pi h cut to the power 1 by 4 e to the power minus half m omega x square, well, 1 by 2h, let's say m minus m omega x square by 2h cut. So this is equals to minus infinity to plus infinity psi 0 star h prime psi 0 dx. This is the original formula, you have just put it, and this is equals to how much? Psi 0 star psi 0, this is a real wave function, so we have to just take the square of it. So m omega by pi h cut to the power 1 by 4 was there, so if you take a square, so this will become 1 by 2, and h prime is equals to bx to the power 4, this is given to you. So this b is a constant, will come outside, minus infinity to plus infinity. What you are left with? This exponential part. So it is appearing twice, means this 2 factor will be vanished. So we have x to the power 4, so we can write it as x square whole square, and e to the power minus this m omega x square by h cut. This 2 factor is vanished by taking square into dx. Now why we have represented it in this form x square to the power 2? Because it is given, the formula to be used is given x to the power 2n, so we have to write x to the power n whole square, something like that. That is why we have written it in this way. Now what is given formula? What is the given formula? It is given that minus infinity to plus infinity x square x to the power 2n e to the power minus alpha x square dx, this is equals to alpha to the power minus n minus half gamma n plus half. This is what it is given in the question. Okay. So for this integral, what we have? N is equals to obviously 2, alpha is equals to m omega by h cut, right? And hence this value E0 first order correction will become m omega by pi h cut to the power half b, and just simply put the formula. Alpha means m omega by h cut to the power minus n minus half, gamma n plus half, so 2 plus half. See how simple it is. Where is Fatima today? Are you there, Fatima? So this will be b times m omega by pi h cut to the power half m omega by h cut to the power minus 5 by 2, and this is gamma 5 by 2. So you can use this form, gamma n plus 1 is equals to n gamma n. Okay, so 5 by 2 means 1 plus 3 by 2, so gamma 3 by 2, and gamma half is equals to root pi. So you can use it in this way. M omega by h cut half minus 5 by 2, how much? Minus 2. So h cut by m omega square we can write. M omega by h cut to the power minus 2, it is h cut by m omega to the power 2, and 1 upon root pi is remaining. Gamma 5 by 2 is 3 by 2, gamma 3 by 2, gamma 3 by 2 is half, gamma half. So this root pi is getting cancelled. So you are ultimately left with 3 by 4 b h cut square divided by m square omega square, and that is matching with option A. Look, is it clear completely or not? Let's solve this problem. The infinite squirrel potential of a particle in a box of size A is modified as shown in the figure below. Assume delta much less than A. Okay. The energy of the ground state compared to the ground state energy before the perturbation was added. Will it increase? Will it decrease? Which option is the correct option? The step before that one in the green color. Yeah, you just put psi 0 star. Psi 0 star means this. Okay. H prime bx to the power 4. Again psi 0 means this. So psi 0 star and psi 0 are same. So it is square of this. So m omega pi h cut square means this becomes 1 by 2. This constant term b is taken here, minus infinity plus infinity. We have to write x to the power 4. So we have written x square whole square e to the power. So it is square of it. So this 2 is cancelled. So minus m omega x square by h cut and dx. Understood now, Karthik? Just put the values of psi 0 star h prime psi 0 and you will get it. Do this one. Look, obviously the previous picture was for this problem, it is an infinite square wave potential. Okay, so it is something like this. Zero to A. Now this has been modified. How it has been modified? It has been modified to this form. Some perturbation has been added, something like this. Look, although the dimension is not looking same, but you have to like imagine. This width, and this width is same. Okay, for the time, for the sake of argument, just know this is A, this is A. This has been applied for delta amount. It is minus epsilon, this is plus epsilon. Got the picture? Actually, this plus epsilon, minus epsilon are the heights. So obviously, if this is 0, this will be delta, and if this is total is A, this is A, right? So what will be this value? A minus delta, right? Is it clear? This point is delta, this point is A minus delta, and this is A. Now you know the normalized wave function ground state wave function of a particle in a box, particle in an 1D infinite potential well of width A each. Psi 1 square root of 2 by A sin n pi x by A. So n is equals to 1. So pi x by A. This is the ground state. So what you have to find out? You have to find out the perturbation. Look, in terms of order epsilon, in terms of order epsilon square, means you have to calculate both first order correction and second order correction. Okay, so let us first calculate what is the perturbing potential. Okay, it is a little bit changed. So given perturbing potential, what is the potential? Perturbing potential means basically perturbation. What is the perturbation? Let's denote it by H prime. So the perturbation says that it is minus epsilon when you restrict yourself between 0 to delta. Okay, it is 0 when you restrict yourself between delta to A minus delta, and it is epsilon for A minus delta to A. Is it clear? So what is the first order correction to the energy? Therefore, the first order correction to the ground state energy first order. So psi 1 H prime psi 1, this is what the formula is. Let me add it in at any step if you don't understand anything. So psi 1 star, so it is 0 to A psi 1 star H prime psi 1 dx. Now psi 1 star psi 1 is square of this. Okay, so 2 by A sin square pi x by A. Now H prime, depending on this range, the value of H prime will be changed. So let's say if I write between 0 to delta, here it is minus epsilon, so this becomes minus 2 epsilon by A sin square pi x by A dx plus, now between delta to A minus delta, here it is contribution is 0, so 0 into this 2 by A sin square pi x by A dx. I am just writing for the sake of completeness. Okay, you can just ignore this second term because you know it is 0, plus it is A minus delta to A. Here what will it become? 2 epsilon by A sin square pi x by A dx. Is it clear? Now you see, what is integration? Integration is like area under the curve. So if you take the integration, you see this is the negative part, this is the positive part. So this should vanish, right? So you can write it minus 2 epsilon by A 0 to delta sin square pi x by A dx plus 2 epsilon by A. If you just change the variable, okay, A minus delta to A, if you just change the variable, it will become 0 to A sin square pi y by A dy. So these two integrations are same, so it is 0. So the first order correction, it is 0. What about the second order correction? If you take second order correction to the ground state energy E12, so you know the formula, m not equals to n. What is n here? N is equals to 1. So m not equals to n is equals to 1, you see the formula psi 1 h prime psi m mod square divided by En 0. So, E 1 0 minus E m 0. So, whatever term it will give you, E 1 0 means the ground state, E m 0 means maybe some higher state. So, obviously this term in the denominator will be negative. Is it clear? Look, E 1 0 is the ground state and E m 0, m cannot be 1. So, it will be more than 1. If it is more than 1, the energy will be more. So, all the time the denominator will be negative because this is the lowest term, E 1 0 is the lowest term. So, some negative term will come proportional to, and this psi 1 h prime psi m. So, if you put psi 1 h prime psi 2, for psi 1 h prime psi 1, that is 0, but if you put 2, 3, 4 and so on, you will get it in terms of epsilon. Okay, epsilon and square is there, so epsilon square. Okay, this is why, because E 1 0 is less than E m 0 for m not equals to 1. So, the second order correction decreases by a term of the order of minus epsilon, then it would have been correct, but it is so option D. Negative sign shows it decreases. So, option D. That penultimate step before 0 this one, look, it is like the area under the curve, it's like A minus delta to A. Okay, so you can see the length, it is A na. So, if you integrate between 0 to delta, it is same na. If you integrate, you should get the area of this portion, right? If the integration limit is minus A minus delta to plus A, then you should get the area. Now, you have just switch the limit from 0 to delta, so it is same na. So, that is why we have just changed the variable. And you do not need this kind of thing. We have given you a short trick, right? What is the perturbation for this? You need to calculate the area. What is the perturbation? You need to calculate the area. The areas are different, so they are cancelling. Even if without calculating this, we can easily say that it will be 0 because it is positive, this is negative. So, and they are equal, they are in equal amount. So, obviously, they are bound to vanish. Is it clear, guys? Yeah. Limits are changed just to make it look like this, the first one. Oh, sorry, it will be 0 to delta, right? You did not tell me. Let's do this one. A 1D box of length A contains 2 particles. So, this is quite important. Two particles, each of mass m, interaction between the particle described by the potential. So this is like perturbation. What is the ground state? What is the ground state energy to the first order in lambda? Can you do this? Look, this integration is also provided 0 to a sin to the power 4 pi x by a dx is equals to 3 by 8a. So here the interaction between the particles is serving as the perturbation, right? The interaction between, look, I am just solving the problem, okay, you are not using your brain. So after the class you should revise it, okay, you should try to understand what exactly the problem is saying. Here also you are trying to understand, but you should, I think, also revise it quite a few times, because these problems are not so much easy. The interaction between the particles can be treated as the perturbation, okay. The Hamiltonian without that will be the unperturbed part. So without the delta potential, look, this is little bit different. Here we used to deal with only one particle, but here inside the 1D box we have two particles, right? Two particles, each is having masses, each is having mass m. So here instead of writing v of x, we will write v of x1 x2. So this is 0, 0 less equals to x1, x2 less equals to a, x1 not equals to x2, okay, and this is equals to infinity elsewhere. Why x1 x2? x1 for one particle, x2 for other particle, two particles are there, right? So unperturbed Hamiltonian will be H0. For one particle, the kinetic energy minus h cut square by 2m d square by dx1 square minus h cut square by 2m d square by dx2 square. So this is for the first particle, this is for the second particle. Okay. Now what will be the corresponding energy for this? energy as well as wave functions. So it will be treated like two-dimensional case. Okay. So E n1 n2 pi square h cut square by twice m a square. So n square pi square h cut square twice m a square was there. So for one particle it is n1 square pi square h cut square divided by twice m a square plus n2 square for the other part. n1 n2 can take the values 1 2 3. Okay, it is equivalent to our two-dimensional case. Psi, their wave function will be the combined wave function psi n1 of x1 psi n2 of x2. So 2 by a sine n1 pi x1 by a sine n2 pi x2 by a. So for ground state, you have to calculate the correction to the ground state, right? For the ground state, obviously the values of n1 and n2 will be 1. So the ground state energy will be E11 11. At zeroth, 0 I am writing means this is unperturbed energy. Pi square h cut square by twice m a square 1 square plus 1 square. So this is pi square h cut square by m a square. And what about the corresponding ground state wave function? Ground state will be psi 1 1. 0 means the unperturbed wave function 2 by a sine pi x1 by a sine pi x2 by a. Okay. Now the perturbation is given by h prime, right? So h prime is equals to how much? Delta lambda into delta x1 minus x2. Lambda into delta x1 minus x2. This is given. So the first order correction to the ground state energy will be, therefore, the first order correction to the ground state energy. Whatever complicated problem you are given, you must stick to the original formula. Okay. Ground state energy E11 correction is first order. So E111. So you have to write the ground state wave function. What is that? Psi 11. Okay. 0 let's say. Then h prime psi 11 0. So we will write the original formula as it is. Now it's the time. Psi 110 is real wave function. So we can write 2 by a, this will appear twice, integration limits 0 to a, this is appearing twice, so square of this. So sine square pi x1 by a sine square pi x2 by a. H prime is this lambda times delta x1 minus x2. Now you see there are two variables, so you have to write the limits 0 to a again, dx1 dx2. Clear? So this is equals to 4 and lambda is taken outside, 4 lambda by a square. Look, 0 to a, we can write sine square pi x1 by a sine square pi x2 by a into lambda of this thing. What we can write? Can we say that, okay, you see sine square pi x1 by a dx1 sine square pi x2 by a dx. So these are equal thing, na? This is 0 to a, this is 0. Okay, let me just do it another step, then it will be clear to you. Sin square pi x1 by a times dx1, and let's say lambda x1 minus x2, let's keep it here, we cannot ignore it, 0 to a sin square pi x2 by a dx2. Actually this lambda x1 minus x2, it is a common between x1 and x2, but you see this integration are literally same. So that is why we can just directly write. It is not advisable to write in this way. I am just, for the sake of understanding, I have just put it in this form, but actually it will be like this: sin to the power 4. Can I write sin square pi x1 by a, and here it is like equivalent to sin square pi x1 by a. So sin to the power 4 pi x1 by a dx1. Can I write it? Because when x1 x2 are equal, then this thing equal, na? Delta x1 minus x2 is equals to 1 when x1 equals to x2. It is 0 when x1 not equals to x2. So we have used this formula. For delta x1 minus x2 equals to 1, x1 equals to x2. So if x1 equals to x2, then you can simply write it. There is no other logic. Okay, simple thing. So this is 4 lambda by a square, and this integration is already given to you in the question. 3 by 8 a. Three lambda by 2a c. Is it clear or not? It's a very interesting and good question. Karthik, Harry, Molly, is it clear? A hydrogen atom is subjected to the perturbation epsilon cos 2r by a, where a0 is the Bohr radius. Change in ground state energy to first order in epsilon h. Simple. You just need to express cos in terms of the exponentials. Ground state energy first order. So what is the ground state energy? E1. First order correction 1. What is the ground state wave function? Psi 1 0 0 for hydrogen atom, you have already talked about it. Then V perturbed is this. So this is your H prime. H prime psi 1 0 0. So you know what is psi 1 0 0? We have also obtained the ground state wave function. As I told you that you should remember the ground state wave function. You see, this question came in CSIR-NET, but the ground state wave function is not given because this is very common. It is a hydrogen atom. The ground state wave function needs to be remembered. That is why they did not provide. But you already know that 1 by square root of pi a naught cube e to the power minus r by a naught. So it's as simple as that. That is why they did not give you the value. If you do not know this wave function, if you do not remember the expression of this wave function, you would have not been able to solve this problem in the examination. Okay. So this will become 0 to infinity psi 1 0 0 because it will involve r and the limit goes from 0 to infinity. Okay, not minus infinity plus infinity, because r runs from 0 to infinity. Okay, if it had x, then we could have written minus infinity plus infinity. For r it is 0 to infinity. Psi 1 0 0 star h prime psi 1 0 0, and you know this is given in spherical polar coordinate, so that is why here we have to write d3 r, not dx. Got it? This is equals to, look, I have used a lot of concept here. If you are a layman, you may not be able to understand, but we have done particle in a box, 1D box, 2D box, 3D box. We have done hydrogen atom problem. So after that we are able to write this, otherwise it may simply confuse people. This is equals to, did you understand this one? If you can understand it properly, then it means you have learned something. Okay, psi 1 0 1 0 0 star psi 1 0 0, same, so 1 by pi a naught cube. Okay, integration 0 to infinity e to the power minus 2r by a naught square of it, so minus 2r by a naught. H prime is psi cos 2r by a naught. d3r is nothing but 4 pi r square dr. Okay, so this is equals to 4 pi, so pi get cancelled, you are left with 4 epsilon divided by a naught cube. Okay, minus infinity plus infinity to the power minus 2r by a naught cos 2r by a naught times r square dr. So we are simplifying it in baby steps, you can say small steps. This is equals to 4 epsilon by a naught cube 0 to infinity e to the power minus 2r by a naught. Cos function can be written in terms of exponential e to the power I 2r by a naught e to the power minus I 2r by a naught divided by 2. This is what the cos formula is, e to the power ix plus e to the power minus ix divided by 2. That is the formula of cos. And this 2 and 4 cancel, so 2 epsilon by a naught cube. You are left with two terms. The first term will contain e to the power minus 2r by a naught 1 minus I into r square dr. Next term e to the power minus 2r by a naught, just try to follow this, it is 1 plus I, because there is a minus sign here, into r square dr. Is it clear till now? Tell me, Mulli, Karthik, Harry, is it clear till now, whatever we have done? Now you can use this formula 0 to infinity e to the power minus alpha x to the power n dx. So this is a very gem formula. We use it so many times. N factorial by alpha to the power n plus 1. Mostly this equation is used in physics problems. So you see 2 alpha 2 epsilon by a naught cube. The first integration n is equals to 2 factorial divided by alpha is how much? You see 2 by a naught 1 minus I, 2 by a naught 1 minus I, because without minus there is alpha to the power n plus 1 means 2 plus 1 cube. The next one, again 2 factorial, here it is 2 by a naught 1 plus I to the power n plus 1, so 2 plus 1. Okay, so this becomes how much? 2 cube, 1 2 is cancelled, so 2 square and this 2, so this becomes epsilon by 2. A naught cube is cutting everywhere, so a naught cube is cancelled, so you are left with 1 upon 1 minus I cube plus 1 upon 1 plus I cube. So what is this value equal to? So you can write it in this way, epsilon by 2 1 by, so 1 minus I into 1 minus I whole square. So 1 minus I whole square is how much? Minus 2I? Plus 1 plus I whole square is 2I. A square plus 2A plus B square formula you see, 1 square minus 2I plus I square, so it is minus 2I. Epsilon by, let's say 2I taken common, so 4I, this one, 1 plus I, 1 minus I, it is how much? Minus 1 minus I plus 1 minus I. Epsilon by 4I minus 2I, 1 plus I 1 minus I is 2, so 2 minus epsilon by 4, option D. All clear, guys, or is it getting heavy? The solution is a little bit lengthy, but overall it is easy. Should I start a new chapter today? Degenerate perturbation theory. Hari, Murli, Karthik. A new chapter, should I start? Okay, let us start a new chapter. So till now we were dealing with time independent non-degenerate perturbation theory. Now let us talk about degenerate perturbation theory. Degenerate perturbation theory. And as from the name it can be predicted that it is applicable when the energy states are degenerate. Degenerate means what? If you have, let's say, an energy level. So if corresponding to one energy level, if there are multiple levels, multiple states having the same energy, then this is called degenerate level. Let's say if you have an energy level En0, so it may have different various levels corresponding to the same energy, means energy of this level, this level, this level, this level are same. So you can say that is phi 1, phi 2 and so on, let's say up to phi f. So this is f-fold degenerate, means the degeneracy is f. Okay. So in case of time independent perturbation theory, what we have seen, this is also part of time independent. Okay, degenerate perturbation theory, this is also part of time independent. In the time independent perturbation theory, how did you write the Hamiltonian? The Hamiltonian of the system can be written as, how do you write H unperturbed part plus the perturbation? We wrote it in this way. This is your unperturbed part, unperturbed Hamiltonian, and this is the perturbation, right? But here in this case, what we are considering here, the energy of the nth state, energy eigenvalue of the nth state. So what will be the energy eigenvalue? En unperturbed, so En 0. We are considering that it is degenerate. How many fold? F fold, means corresponding to one energy level there will be f number of levels which have the same energy, okay, which is f fold degenerate. And the corresponding degenerate eigenfunctions are phi 1, phi 2, phi 3 and so on up to phi f respectively. Same energy as En, means this state is having energy En0, this state is also having energy En0, this state is having energy En0, this state is also having En0, this state is also having En0. All of them are having the same energy. The states are different. I mean, I have just represented it for the sake of visualization. Okay, it is not like their energies are different, they are having the same energy. Now we have to find out the correction in energy. So when we will calculate correction in energy, the energy values will be different for different, that is why they will be splitted. Okay, that is the concept of splitting. So you imagine it in this way, this is the after because of the perturbation effect. So you can imagine you have f number of threads. Yeah, threads, you know, thread. So when I am talking about the same energy level shared by the 7 threads, so 7 threads are combined together. Okay, all of them are having energy En0. But because of the perturbation, what will happen? Their degeneracy will be lifted up. So the purpose of perturbation is to introduce the energy difference between the level. Because if En0, let's say it is, let's say 7-fold degenerate. And for an example, 7-fold degenerate. So their energies are same. So they will appear to be one line, right? But the perturbation will induce some correction to the ground state energy values, and this will give you slightly different 7 different values. It may be 7 different, or some values may be equal, some values may be different. 7 different values means it is complete lift of degeneracy. Okay, so this degeneracy was there, but it was not lifted. Because of perturbation, the degeneracy is lifted. Understood? So they will appear as 7 different levels. Is it clear or not? Tell me. Let us try to understand it. En0 is a single level. Okay. Now the first order correction due to perturbation, En1, that is not single level. That will give you, let's say, 7 different values. Okay. And you know the total energy is calculated by adding this En0 with this correction. So if this En1 is different, 7 different values will get, 7 different levels will get. So previously it was 1 degenerate level. The perturbation is just lifting the degeneracy. Okay, this is the overall concept. Suppose the energy correction due to perturbation H prime is En1. Okay, first order correction. Then En1 can be calculated by solving the following equation containing secular determinant. On the left hand side. Look, how many different values we are expecting. What is just happening? As I told you, if there are it is f-fold degenerate, so f values we are expecting. So how can we get this 7 values or f number of values of En1? This can be determined from this one. You see, H prime is the perturbation. So it will be written in the matrix from H11 prime minus En1. So En1 is the eigenvalue. H22 prime minus En1. And it will go on finally H FF. So it will be an F by F matrix. Follow the other one. H11 prime, this will be H1 2 prime, then H13 prime and so on, H1F prime. Here it will be H21 prime, then this, so on, H2F prime, will so on. Here what will be the value? HF1 prime, then HF2 prime and so on, HFF prime minus En1 prime, where this H, let's say Mn prime. What are the term? It is calculated from phi m h prime phi n, simple as that. So it is the matrix method you have to use. So obviously, how many different values of En1 you will get? It will be the eigenvalues of this, right? And if it is a f by f matrix, you will get f number of eigenvalues. Now, if all the f eigenvalues are distinct, different, then you will get 7 different, let's say f different levels having different energy. If few of them are equal, then you will get lesser lines than f. So perturbation lift complete degeneracy or it lifts partial degeneracy. If the sum of the eigenvalues are equal, then it will be partial lift of degeneracy. If all the values are distinct and different, it will be the complete lifting of degeneracy. So lifting of degeneracy means previously, let's say you had it was f-fold degenerate, and it is just by applying the perturbation they are getting separated because of the correction in energy. So this is the job of the perturbation. Did you get it? Here maybe Zeeman effect is one of the example of this. Okay, na? Here what is the perturbation in Zeeman effect? Magnetic field. Stark effect. What is the perturbation in a Stark effect? Electric field. Why we subtract only diagonal? So because they have some subscript. No, actually we need to calculate the eigenvalues. So the way we calculate eigenvalues, so that is why it is subtracted, you know, a minus lambda I, same energy as E1. No, understood. So it is like this is En0 and these levels are maybe En0 plus. Look, En1 will have 7 different En1, look, let's assume that En1 will have different values. For the time being, let's take 7 different values, say EA, EB, EC, ED. So En0 plus EA, let's say, then En0 plus EB. So they are different, and that is why we get different lines. Everything is understood? Now focus on this one. H0, this is the unperturbed Hamiltonian. Phi n alpha, this is the unperturbed eigenstate. En0, phi n alpha. Okay? Alpha is equals to 1 to f. Why? Because En0 was degenerate state. So it has f number of state, as I told you. So phi n alpha. So it is like phi n1, phi n2, phi n3 up to phi n f. Alpha stands for one or more quantum number. The energy eigenvalue En0 are independent of alpha. In the zeroth approximation, we can write as psi n0, psi n as the linear combination of phi and alpha. Obviously, we can write it psi n linear combination of a alpha, phi and alpha. Considering phi and alpha to be orthonormal state, we can write phi and alpha, phi and beta is equals to delta alpha beta. Psi n is normalized, so psi n is equals to 1. Then we can get the coefficient alpha is equals to 1 to f, E alpha mod square equals to 1. So this is quite straightforward. We have already talked about it. Then this is En alpha. En alpha is equals to En0. This is the unperturbed energy plus the correction. En alpha of 1. Okay. Now different alpha can take values 1 to f. So you will get different values of energies, En0 plus En1 1, En0, En2, they are first order correction but different values, and so on. En0, Enf of 1. The roots En alpha of 1 are in general different. In case the eigenvalues of H are not degenerate, the F full degenerate level En0 of the unperturbed level is splitted into F different levels. That is why we say that the perturbation lifts the degeneracy. The lifting may be either total or partial. Just a moment. आपको पानी लेना, पानी देते हैं, पानी देते हैं। मेरे में तो है अभी पानी। हाँ आप खाएंगे, आप लोग खाएंगे। वो इसको देते हैं ना, तारी जी को देते हैं ना। तारी के राहुल तारी हाँ तारी जो ऊपर रहता है। हाँ ऊपर होते नीचे में वो जो राहुल। तो अभी तो मेरे पास खाली नहीं। तो राहुल यहीं पे रखता था। एक अगर जार देना है रख दें। तो वही लेता था, राहुल लेता था। ये ताई जिसे मिल गया। ऊपर नहीं रखता है। हाँ कॉल करना है। मैं क्लास कर रहा हूँ। Sorry guys. So you see, the purpose of the perturbation is to lift the degeneracy. If all the values are distinct or different, then it is the complete liftment of degeneracy, complete lifting of degeneracy. The lifting of degeneracy may be either total or partial. Total means 7 or F different values, whether all roots of En alpha 1 or only some of them are different. So it may be partial lifting or complete lifting. Did you understand the theory overall? The problem solving part is quite easy, don't worry about that. So here let me just summarize everything. So in summary, to determine the eigenvalues to first order and the eigenstate to zeroth order for an F-fold degenerate level from perturbation theory, we proceed as follows. First of all, we need to formulate this matrix. For F-fold degenerate level, determine this F by F matrix of the perturbation. HP, once you calculate HP, you can calculate it by calculating this matrix element phi n alpha, HP, phi n beta. Once it is done, you can easily calculate the eigenvalues, diagonalize this matrix and find the F eigenvalues and their corresponding eigenvectors. This is what it is. And once you get the energy eigenvalues, you can calculate the total energy. This is the unperturbed energy plus the perturbation. The corresponding eigenvector can be written in this way: psi n alpha beta is equals to 1 to F A alpha beta phi n beta. Okay. Does the perturbation cause degeneration? No. Perturbation just lifts the degeneracy. Degenerate level exists, na? Degenerate level exists in general. So the job of the perturbation is to separate it. Let me show you one problem, then it will be more clear to you. Consider a two-dimensional infinite square well potential. Okay. Normalized eigenfunctions are given. perturbation is given V naught, then the correction to the energy of the first excited state. The ground state energy is non-degenerate, but first excited state is degenerate. No? You know, Nx, Ny, 1, 2, 3. So if you talk about the ground state is Nx is Ny equals to 1. This is a ground state. So this is non-degenerate, right? Non-degenerate. But if you talk about the first excited state, then Nx is equals to 1, Ny is equals to 2, Nx is equals to 2, Ny is equals to 1. So this is doubly degenerate, right? So for this we cannot apply the non-degenerate perturbation theory. We have to apply degenerate perturbation theory. This will give you, let's say, phi 1, this will give you, let's say, phi 2, and you can easily calculate the matrix element. Okay, just try to focus, try to follow what we are doing. You understood the concept, right? So you have to calculate the correction to the energy of the first excited state. So first of all, what is the energy expression? The energy of the nth state for the 2D infinite square wave. Let's write En, nx square pi square h cut square by twice m a square plus ny square pi square h cut square by twice m a square. So does it mean in degenerate type questions we have the word correction to the energy of the first excited state? It not necessary first excited state, it may be, it will depend in which state it is degenerate. Like it will never give you for the ground state, because ground state is non-degenerate. Okay, if it is degenerate, then only it will be applied. You can easily understand. If we see this word first excited state, we can assume simply it is the degenerate perturbation case. Not necessarily. If you consider let's say 1D case, for 1D case all the states are what? Non-degenerate. So for 1D case you will not apply degenerate perturbation theory. But if you choose n equals to 1, it is non-degenerate, n equals to 2, non-degenerate, n equals to 3, non-degenerate. But for 2 dimension we get degeneracy, right? So it will depend. First excited state means we have to consider first excited state. If it is talking about other state, then we have to consider whether it is degenerate or not. If it is degenerate, then we will apply degenerate perturbation theory. So the energy of the first excited state, we can write it in this way. Energy of the first excited state. This is equals to 5 pi square h cut square by twice m a square, and this state is two-fold degenerate. Okay, f is equals to 2, two-fold degenerate with, you see, nx ny, it is equals to, you can take 1 2, then also you get 5 a pi square h cut square twice m square, or if you take 2 1, then also 2 square plus 1 square is 5. So correspondingly we can choose the eigenfunctions. Okay, so what is phi 1 here? Phi 1 is the state by taking nx is equals to 1, ny is equals to 2, right? So wave function you can see, 2 by a sin nx pi x by a sin ny pi y by a. So if you take 1 2, then it is 2 by a sin nx means 1 pi x by a sin ny means 2 pi y by b. Sorry, a is there, b is not there, equal. So to make our task easy, what will be phi 2? 2 by a sin 2 pi x by a sin pi y by a. Is it clear? So we will construct the secular determinant now. What will be the secular determinant? Equating the secular determinant to 0, we get, look, it is h11 prime minus e1 first, okay, let's denote it by e prime. Okay, the first excited state is e prime, correction to the first excited state is e prime. h11 h12, it is only two-fold degenerate, so it will be 2 by 2 matrix. So h11 h12 h21 h22. This is equals to 0. So what you can write? h11 is what? Phi 1 h prime phi 1 minus e prime h12 phi 1 h prime phi 2 h21 phi 2 h prime phi 1 h22 phi 2 h prime phi 2 minus e prime. Now we have to calculate these terms one by one. So this will get a little bit lengthy, but it is okay. You have to understand. Let's calculate this first term, phi 1 h prime phi 1. This is equals to phi 1. It's a two-dimensional function. So minus infinity plus infinity minus infinity plus infinity. Phi 1 star h prime phi 1 dx dy. Understood? Now what is h prime? H prime is given to you. It is v naught between 0 to a by 2, 0 to a by 2 for x and y. Okay. V naught 0 to a by 2. Phi 1 star, phi 1 same 2 by a sin square pi x by a sin square 2 pi y by a. Now you see here it is a function of y and that was a function of x. So 0 to a by 2, here you have to write dx. Another 0 to a by 2, this is dy. Is it clear or not? So what value will you get? You will get V naught by 4. Are you getting V naught by 4 or not? In a similar fashion, similarly, if you calculate, let's say H2, I2, H prime, I2, this will be minus infinity to plus infinity, phi2 star, H prime, phi2 dx dy. This will also give you V naught by 4. You can calculate it. Phi 1 H prime phi 2 minus infinity to plus infinity, phi 1 star H prime phi 2 dx dy. This will be equals to V naught will come from H prime 0 to a by 2, 2 by a whole square will come, phi 1 star, so sine pi x by a sine 2 pi y by a, phi 2 sine 2 pi x by a sine pi y by a, then dx dy. Again, you can just separate these integrations, V naught by a square, x part 2 sine pi x by a sine this 2 pi x by a dx, other part sine 2 pi y by a sine pi y by a d. This 2 square was there. Acha, here we made a mistake. It is 2 by a whole square, right? Because phi 1 itself has 2 by a, so phi 1 star phi 1, so that will be 2 by a whole square. Any question, guys? Batao. Any point you did not understand, tell me. Just tell me, I will make you understand. Actually, we can just simply expand it. Look, V naught will come. 2 sin square theta is equals to 1 minus cos 2 theta. So it will come a by 2. Okay. From the next integration, it will come a by 2 and 1 by a square is there. So that is why it is V naught by 4. No question? Very good. So this is equals to V naught. Look, V naught by a square and this integration 2 sin a sin b. This is also 2 sin a sin b. So you can apply the formula and you will get 4 by 3 pi 4 by 3 pi, this will become 16 V naught by 9 pi square. Okay. Now let me just show you the calculation how this is coming. So star, let's say I am showing you one example, 0 to a by 2 cos pi x by a minus cos 3 pi x by a dx, whereas 2 sin a sin b is equals to cos of a minus b minus cos of a plus b, right? Let's make it more simplified. 2 sin a sin b, so cos of a minus b minus cos of a plus b. Okay, so you will get the first integration a by pi sin pi x by a minus a by 3 pi sin 3 pi x by a. The integration limits are 0 to a by 2. Now if you put a by 2, so a by pi plus a by 3 pi, next x equals to 0 gives you 0. So this is a by 3 pi, 3a by pi, so 4a by 3 pi. So 4a by 3 pi, 4a by 3 pi. So let's make it 4a by 3 pi, 4a by 3 pi, this a square. So that is why 16 b naught by 9 pi square. How infinity becomes 0 to a by 2? Very good question. How infinity becomes 0 to a by 2? Because h prime is non-zero only between 0 to a by 2 and 0 to a by 2. 0 otherwise. So if something is 0, so everything will be 0. So only this part 0 to a by 2 will give you non-zero. Okay, because of h prime we wrote the limit 0 to a by 2. Any more question, guys? Now we got all the values of the matrix h11 prime, h12 prime, h21 prime, h22 prime. So let's put them. Therefore the matrix becomes h11 prime, we have got v naught by 4 minus e prime, h12 prime 16 v naught by 9 pi square, h21 here also it is 16 v naught by 9 pi square, here it is v naught by 4 minus e prime, this is equals to 0. So this is equals to v naught by 4 minus e prime square minus 16 v naught by 9 pi square whole square equals to 0. So a plus b, a minus b. So v naught by 4 minus e prime is equals to plus minus 16 v naught by 9 pi square. You can also do a plus b, a minus b, so it is the same. So e prime, it will give you two values, v naught by 4, okay, minus plus 16 v naught by 9 pi square. So minus plus plus minus same thing, 1 plus minus 64 by, so v naught we have already taken common, so we are left with 64 by 9 pi square. Option B. Look, this solution is quite lengthy, but it is in the syllabus, so we have to do it. Tell me, guys, if any question is there. ऑल क्लियर, आगे बढ़े. Let's do another problem. This one, this came in December 2014. The Hamiltonian H naught for a three-state quantum system is given by the matrix H naught is equals to this when perturbed by H prime. Perturbation is itself given H prime. Okay, in the matrix form, itself given in the matrix form. Epsilon times this. The resulting shift in the energy eigenvalue of E naught equals to 2. You see, it is quite straightforward. H0, it is a diagonal matrix, so the eigenvalues will be 2, 2. So it is degenerate eigenvalue, right? It is degenerate eigenvalue. That is why you have to calculate the resulting shift in the energy eigenvalue of E naught is equals to 2. How will you do this? So here, what is the unperturbed Hamiltonian? Unperturbed Hamiltonian. You have to revise this class 2-3 times, okay? Otherwise you may not be able to understand. These are little bit difficult topic comparatively. 1 0 0 0 2 0 0 0 2. Okay, this is unperturbed Hamiltonian. And what about a perturbed Hamiltonian? Perturbed Hamiltonian. Perturbed Hamiltonian is H prime epsilon times 0 1 0 1 0 1 0 1 0. I am sounding like a robot. Epsilon much less than 1. So unperturbed Hamiltonian will give you the energy eigenvalues as follows. The unperturbed Hamiltonian has unperturbed energy eigenvalues E0 is equals to, the diagonal elements are the eigenvalues 1 2 2 1 2 2, out of which E0 is equals to 2 is a degenerate eigenvalue. Degenerate eigenvalue having degeneracy 2. Okay. Now the corresponding eigenvectors, you can calculate the eigenvector using the way you find out eigenvector and eigenvalue. Okay, so corresponding normalized eigenvectors are, so it is very easy to predict. Let's say I am writing psi 1 instead of phi 1. It is 1 0 0, psi 2 0 1 0, psi 3 0 0 1. Okay. E0 equals to 1, then 2, then 2. So 3 eigenvectors you will get. So you can say that corresponding to E0 equals to 1, it is this. This is corresponding to E0 is equals to 1. This is corresponds to E0 is equals to 2, and this is corresponds to E0 is equals to 2. You know, the eigenvalues may be same, but eigenvectors will be different, so that is why they are different. Okay. So if we consider, let's say E0 1, this is the energy correction due to the perturbation. Then what you can write? let's write E1. Okay, because ground state other than the harmonic oscillator, everywhere it starts from n equals to 1. So we have to formulate the matrix. What is the matrix? Look, H prime 1 1 prime minus En1 H. Actually, you see, look, here we need to understand one thing. It should have been a 3 by 3 matrix, but we are mainly focusing on this one. So which part we are taking? We are only taking this part. Okay. So that is why we are writing it H22 prime, then it is H23 prime. This is H32 prime. This is H33 prime minus En1. This is equals to 0. Is it clear or not? Because we are looking for two values of the correction. So only that below part is taken. Understood? This part. Now what is H22 prime? It is psi 2, H prime psi 2. Psi 2 is bra psi 2. What is bra psi 2? Ket psi 2 is 0 1 0. Bra psi 2 will be row matrix 0 1 0. H prime. H prime is given to epsilon times 0 1 0 0 1 0 1 and 0 1 0. What is ket psi 2? Ket psi 2 is 0 1 0 column matrix. So if you calculate epsilon 0 1 0 and this multiply, if you do, you will get how much? 0 1, so 1 0 1. So this is epsilon 0 0 0 0. Okay, let's calculate H23 prime. H23 prime psi 2 H prime psi 3. Psi 2 ket, sorry, bra 0 1 0 H prime epsilon 0 1 0 1 0 1 0 1 0. Psi 3 ket 0 0 1. So what you will get? Let's keep epsilon, then 0 1 0, then multiply this 2. Multiplying this 2 will give you 0 0 0 0 0 0 0 0 1 0. It will give you 0 0 1 1. Okay. H32 prime psi 2 H prime psi 2 psi 3 H prime psi 2. Bra psi 3, so 0 0 1 row vector epsilon 0 1 0 1 0 1 0 1 0. Psi 2 bra sorry ket psi 2 ket psi 2 ket psi 2 0 1 0. So again, what will it give you? It will give you epsilon. Next, H33 prime psi 3 H prime psi 3 psi 3 0 0 1 epsilon 0 1 0 1 0 1 0 1 0 psi 3 again 0 0 1. This will give you 0. You can multiply. Okay, multiply the last two, whatever product matrix you will get, you will just multiply with the first one, and as a result of that what you get, look, h11 prime we have got 0, so 0 minus e1 1, h which was h23 prime, right? h23 prime we got epsilon, h32 prime epsilon, h33 prime 0 minus e111, so e11 square minus epsilon square equals to 0 means e111 plus minus epsilon. That's precisely matching with option C. So simple. So simple, so simple. Any question, guys? Tell me if anyone has any question with this problem. And with this we come to the end of this lecture, and on the next day onwards we will go for time dependent perturbation theory. Time independent perturbation theory is over, we will go for time dependent perturbation theory. Any question? There is no question. Bye bye, take care, have a great day, bye. Revise it, okay?